Right now, across the globe, millions of voice conversations and thousands of high-definition video streams are taking place simultaneously. To manage this massive flow, networks rely on an engineering technique called multiplexing. This allows completely different streams of information to merge into a single shared transmission line, travel together, and arrive perfectly separated for their respective recipients. Pulling off this routing requires highly complex switching mechanisms, but engineers face a difficult biological and mechanical reality. Not all of this information behaves the same way. Take a standard human phone call. Our voices require a continuous, uninterrupted flow of information. The words have to arrive in strict sequence, and the connection cannot tolerate delays, otherwise the conversation breaks down. But computer data operates entirely differently. It is what engineers call bursty. It transmits in rapid, intense spikes of activity, like downloading a massive file, followed immediately by periods of absolute silence while the machine processes the information. This creates an inherent structural dilemma. How do you design a single physical network that supports the rigid, delay-free demands of human voice without squandering physical resources during the long, silent pauses of computer data? To see how we route a voice conversation, we look to circuit switching. Before a single word is spoken, the network executes a setup phase, locking in a dedicated physical link between caller and receiver. This exact logic powered early telephone networks, where operators physically plugged cords into switchboards, forming an unbroken electrical circuit from point A to point B. Reserving an entire path guarantees perfect sequence for voice. But for modern computer data, the network efficiency completely collapses. Circuit switching holds maximum bandwidth open for the entire session, but bursty data only takes tiny slivers, wasting massive space. It also creates a vulnerability. If a single node fails on this pre-established route, the severed connection must be rebuilt from scratch. Circuit switching delivers perfect order, but its strict monopolization of network resources makes it incredibly inefficient for an internet dominated by unpredictable bursts of data. That brings us to our second transmission, a computer file. To handle this, the network uses packet switching. Instead of sending the file whole over a reserved line, it is cleanly shattered into small, self-contained units called datagrams. Each datagram carries its own destination address. They are fired out into the shared network infrastructure, left to navigate the medium independently. Their path is guided by routers, intermediate nodes along the network, that read each address and make split-second forwarding decisions to push data closer to its final destination. This network map shows dynamic routing solving the wasted space problem. Unreserved packets seamlessly interleave into a single pipeline, maximizing capacity. It also provides resilience. If a central router shuts down, subsequent datagrams automatically adapt, finding alternate pathways around the blockage. Engineers eventually developed a hybrid called a virtual circuit. This optimization allows the network to pre-establish a route and assign it an ID number, bypassing split-second routing decisions at every stop. But unlike the rigid lines of circuit switching, a virtual circuit still multiplexes at the router level, meaning multiple connections can actively share the exact same physical hardware simultaneously. Packet switching abandons the safety and guaranteed order of a dedicated line. It embraces a chaotic environment to achieve maximum efficiency and an architecture that can survive physical damage. Deep inside the server racks, the modern internet is an engine of controlled chaos. Data is constantly shattered, scattered across shifting routes, and arriving at its destination entirely out of sequence. To gain the resource efficiency and survival capabilities of packet switching, engineers accepted the loss of a guaranteed sequence. They offloaded the responsibility of order away from the physical cables entirely. That responsibility falls to the transport layer, specifically a protocol called TCP. Sitting quietly at the destination device, TCP catches these delayed, out-of-order packets, perfectly reassembling them into their original sequence. It is this invisible software shield that hides the frantic, fractured reality of network routing. It protects the user from the chaos of the backbone, giving us the illusion of a flawless, continuous connection every time we click download.